All right, everyone. I am super excited to be here with Pieter Abbeel. Pieter is a professor at UC Berkeley, where he's co-director of the Berkeley Artificial Intelligence Research Lab, or BAIR, as well as co-founder, president, and chief scientist at Covariant. Pieter, welcome back to the TWiML AI podcast.
Sam, really good to see you again. Thanks for having me.
It is really hard to believe that it's been just under 4 years since you were on this show. You were your interview was number 28, and we're approaching 500 now.
What a journey.
What a journey. You've been up to a lot of cool stuff, including starting your own podcast. We'll talk a little bit about that. But since it's been so long and you've been up to so much, why don't you take a few minutes and share with our audience a little bit of background and what your primary research interests are?
Sure. Yeah. So 4 years ago, long time. So a lot has happened since. The things I'm mostly thinking about these days are kind of twofold. One is with my Covariant hat on as co-founder at Covariant. At Covariant, we're trying to bring AI robotics into the real world. So take it out of the lab, out of simulation, and make robots do things for us in the real world. And so a lot happening there, and looking forward to talking more about that with you, Sam. And then my other hat at Berkeley, we're doing academic research in AI and robotics. And I would say some of the things we're most excited about these days are work at the junction of unsupervised learning and reinforcement learning, where, of course, unsupervised learning is where the learning happens without any annotation of the data, which is nice because it can be a lot more efficient that way, no annotation needed. But then reinforcement learning, the trial and error learning that can allow a robot to acquire skills from its own experience, its own practice. And so the combination of those two is where we're spending a lot of time right now at Berkeley.
Awesome. And we'll dig into both of those areas in detail. But before we do, for those who didn't catch your podcast 4 years ago or don't know your story, how'd you get into robotics?
Sure. Yeah. So for me, in some ways, it didn't start in robotics per se. It started with artificial intelligence, the kind of brain behind the robots. For me, it was, well, when I was in undergrad studying all kinds of things, it just seemed everything was interesting. But it also seemed that to do well, you got to pick something to specialize into. And so the question was, okay, what is going to be the most interesting thing to spend my time on? And for me, it became pretty clear that it's so intriguing that we as humans can think. It's kind of what sets us apart, I would say, mostly from other animals, is that we can think deeper, harder than most animals. And so that to me was so fascinating. And of course, the first thing you might think is, okay, then study neuroscience, because that's studying how the brain works. But that discipline fascinating, but it just seems so hard to make progress on, to dissect the brain and understand how it works. So difficult. So I figured try to engineer something that thinks. Seems more natural as a way to make some progress and get closer to what we're doing as humans when we're thinking.
Do you follow neuroscience research at all? Does that inspire you?
Oh, there's a lot of things in neuroscience that have inspired me. I think it's really interesting. The thing that maybe inspires me most these days is these findings about how general the human brain is. So there are these studies from several years back now, where it was shown that, you probably heard this before, Sam, but it was shown that you can, for example, put the electrode pattern on a person's tongue, and this person can be blindfolded or can be blind. And if the electrical pattern on your tongue is activated in the same kind of pattern as an image that you would see with your eyes, your brain can learn to process that and see. And they had this demonstration where somebody was effectively rock climbing while seeing through their tongue. And so this kind of thing to me blows my
That's
mind that
amazing.
the brain is so general. What you use for taste input can be used to see. And so, yeah, I think it's really inspiring to go that direction of generality.
Absolutely. Absolutely. Let's maybe start with talking about what you're up to at Covariant. I think the last time we spoke, if I remember correctly, you were a year or so out from founding Covariant.
Yeah. So last time we were a little, well, yeah, still about a year before we started Covariant. And what happened is we started seeing this trend that it seemed a lot of progress had been made by us and by many others on building more intelligent robots. And that always seemed the missing piece. If you look at robots out in the world that are doing useful things for us, you go to a car factory and you look around, it's amazing. So many robots, right? And they're building cars, and that's amazing. But if you look at the details, these robots are doing the same motion effectively over and over and over. Very diligent, but also um, it requires a lot of structure. Most problems cannot be solved by just repeated motion.
Hmm.
And so it seemed 3, 4 years ago, it seemed that maybe time had come where we can make robots smarter. Enough research progress had been made to start taking on bringing this to the real world, to give robots the ability to think, and see and think and react to their environment rather than just following pre-programmed motions. And that seemed just like it would open up so many more opportunities than what was possible until then. And so that was for us really the trigger to this notion. Okay, we think we can start building robots that can see, react, think, and do many more things than pre-programmed robots can do.
Now, the opportunity for robots that can think is obviously quite broad. Are
Hmm.
there specific tasks or problems that you're going after? Is this the classical pick and place kind of robotics problem, or are you beyond that? How do you think about the problem domain?
It's so interesting you bring that up because you say pick and place, right? And it's exactly what we're looking at, but it's not how we started out. So we started out and we said, let's do a full investigation of what are the most pressing problems when we talk with manufacturing companies, with warehousing companies, with agricultural firms, and so forth, construction. And we spent the first half year of Covariant talking with about 200 different companies and getting a sense for essentially if you could have a really smart robot that, given its physical form factor, a standard industrial robot, but if
Hmm.
it were smarter, what would it be able to do for you? And many, many things people wanted robots to do, but it became also very clear that in logistics slash warehousing, distribution centers, e-commerce fulfillment, that's where everybody was just hurting for help. They wanted robots to come help. They had already automated what effectively is done with legs. They're running around the warehouse. A lot of people know about the Kiva robots at Amazon that can go
Hmm.
under shelves and bring shelves to people. There's other systems too, but the same idea that the leg work has been automated, but that's a structured automation problem. It's not an AI problem in the same way that we're looking at AI these days. But the handwork, what people do with their hands, it just there was no automation for it, and they want it. They want to complete that automation process of these warehouses. And after 6 months, it became so clear to us that's the problem we need to focus on at least first, and hopefully we can generalize from there, and we think we will. But that's how our initial focus is effectively pick and place type solutions for warehousing, logistics, fulfillment, and so forth.
Mm. I'm imagining that a lot of the progress in that domain to date has been adapting the robots to the very specific form factors of the problem that someone is trying to solve. We've got these boxes. We're going to align these boxes in this way, and so then the robot can play some smaller part. And maybe a part of what you're trying to do is loosen those constraints by making the robots smarter and more agile in their ability to manipulate in the real world.
That's exactly right. So when you go into a warehouse, there is already a lot of conveyors and mobile robots and so forth that bring things where they generally need to be, but they don't bring individual items. They tend to bring shelves or boxes. And then the next step is for either a worker or a robot to look into that box and pick out the one item that's needed to fulfill the next order. And to do that, you actually need a very general kind of capability. And I think that's probably a bit surprising to many people who are not familiar with warehouses, but many of these warehouses have millions of different SKUs, which are stock keeping units. And these SKUs also turn over very quickly. They have different packaging and so forth. So it's not enough to say, oh, these are the SKUs. I'm just going to set up a system that's ready for these specific SKUs. You actually need to somehow build a AI system that understands the general notion of object, that can look at a box, items in the box, especially the box itself is easy, but the items in the box, and understand, oh, there are items there, and there's an item over there, another one over there, there's overlapping items there, and that's the one I want to pick, and here's how I'm going to pick it, where I'm going to place my suction cup or my gripper, and this is how I'm going to maneuver it out of that box without flinging anything else out of the box too.
Mm-hmm.
And for us as humans, these things are very simple to do. You can do them without thinking. You can be, maybe listening to a podcast or something while you're doing this and thinking about what's being talked about there. But to get a robot to do that is actually really, really hard. It's one of those things where, sure, it's not too hard to get, 80% success, but to get to the levels of autonomy that you need to be trustworthy in a commercial setting, several nines of reliability, 99.9% and above, all of a sudden becomes really, really hard because this system now needs to understand pretty much any situation it encounters. And while most people are probably not so familiar with warehouses, it's very similar to self-driving cars. We've had demos of self-driving cars for 10 years or longer, and the demos today don't necessarily look all that different if you watch a 1 minute, 2 minute demo of a self-driving car, but they've become more reliable, but it remains very hard to get to perfect or near perfect reliability, of course. That's the challenge, that long tail of always new things you can encounter, either as a self-driving car in that domain or as a warehouse robot, where you're always seeing new items, new packagings, and somehow you need to make sense of that and reliably pick in place.
It's maybe an interesting analogy. I'm thinking of many folks in the field. Maybe Andrew Ng is one of the most well known who has kind of talked about this view that self-driving cars will first happen when we constrain their environment. Maybe the autonomous bus lane in an airport, as opposed to general self-driving ability. We've already done a lot of that work in the industrial realm. You've talked about the conveyor robots and how we've really constrained that environment. Is there, does that say that maybe that's not going to be enough even for self-driving cars, or is that, pushing the analogy too far?
Yeah, I think it's a really good question. The self-driving car side of things, is it possible to create real value within constrained environments? For example, the natural one would be lanes dedicated to self-driving cars. That might make it much easier, probably would be much easier, but at the same time, I mean, where are those lanes? Do they mark them? Trains are like that, of course, and I mean, trains, not to step on the railroad tracks because that's dangerous. That's not where you're supposed to be, right?
Mm-hmm.
And so definitely I could see a version of, if you go that far and really delineate this is self-driving car territory only, I suspect today's technology would probably create a lot of value, but at the cost of a lot of real estate being taken up by those dedicated tracks and so forth. Probably what I see happening there, but of course I'm not the one pushing self-driving cars personally, but have a lot of friends doing that. It seems highways, is sufficiently constrained because typically people aren't walking around there, and everything is cars and motorcycles. So there
Yeah,
are constrained environments there.
I think what I'm wondering is if, and this is maybe a bit of a tangent, but are there things that you've learned in your experience in factories that inform how you might approach the self-driving car problem and this whole constraining the environment if you were to decide to go try to solve that problem tomorrow?
No direct lessons in that way, but I think there's a very strong analogy in a different way, which is the chasing the long tail of events,
Mm.
whether it's items or configurations of items or it's traffic situations. The kind of getting 80% coverage isn't too hard. That's very feasible with a relatively fast effort, but getting to the reliability that you need to actually function, well, there's this long tail of things that you barely ever see. Each one of them you barely ever see, but when you add it up together, there's a lot of it. And so you need to somehow observe all these rare events that together add up to non-rare probability mass. So that's why it's so important. If it's just one rare event that happens once in a million years, who cares? But if there's a million of those events that happen once in a million years, all of a sudden every year you have an event, right? And that's kind of what's happening. Is there is this long tail of very rare things that you somehow need to train your neural networks. In most cases, I imagine self-driving people train neural networks too, but definitely for us at Covariant, train your neural networks to have a more general understanding of objects, their shapes, their graspability, their interactions when they're in a bin, when you try to pick one out, or when you place, how that interacts with each other. Understand that for every scenario you might encounter without having the ability to train on every scenario. You need to train something that generalized. And I think that is kind of the case in both situations, whether it's self-driving or warehouse picking. You need that generalization ability.
I remember from our last conversation, you were very staunchly for end-to-end deep learning. And I wonder if your experience solving problems in the real world and industrial domain has changed that at all. We had talked about end-to-end versus, ensembles and incorporating physical knowledge of the world, that kind of thing. Do you still feel as strongly about, a single end-to-end deep learning model?
So I think, yeah, you're absolutely right with your observation about what we chatted about last time. And maybe I've adjusted things a little bit, but I'm still very close to where I was last time. So first of all, I would say there are two different things to think about. So one thing to think about is research, academic research. When you write papers, where do you think most of the novelty, surprises, new things are going to be? And my sense is that while on the other hand, when we put things in the real world, often complementing it with prior knowledge you have from physics and so forth can give you a stronger system. From a purely research academic point of view, my sense is that those more classical approaches have been researched so well already that there is less room to push the boundary in terms of novelty and surprises and things that, oh wow, didn't expect this to be possible, and now a computer, AI, robot can do this. And so in the academic realm, I'm really big on going as purely on learning as possible because there's the most novelty there. On the more practical thing, which you're of course alluding to, it's stupid to throw away anything that has guarantees and is guaranteed to work if you know that you have maybe a 3D understanding of the environment. Well, the notion that the environment is 3D and that you can build a 3D map of it, and or at least a depth map or whatever you want to build, it seems stupid to not use that kind of notion and just say, hey, we'll never tell the neural net explicitly that 3D matters. It seems a waste of.
It even sounds crazy saying it.
Yeah. That said, here's one thing that we found. I think that ties into this, which is the tricky thing with coding in prior knowledge is that it's very hard to be super precise about prior knowledge. And so whenever you think you're encoding prior knowledge, you might be encoding something that's actually slightly untrue, slightly incorrect in some situations.
Can you give an example?
So let's say, here's a simple example. Let's say you say, hey, a good way to pick up an object is go to the middle of a flat region with a suction cup. Go to the middle of a flat region. That might seem like a good heuristic, and say, okay, that's where you should go. And obviously, if you code that in from day one, it'll work better than if you say, hey, just learn where to pick something, because now it has to figure out that the middle might be better than an edge and so forth. But the downside of hard coding in that the middle is a good spot is now all of a sudden maybe have overlapping objects.
Mm-hmm.
And maybe the middle is not a great spot to reach, or you need to kind of slide things out another way, or maybe it's an object that has a center of gravity that's not even close to the middle. Or maybe there is a way to place multiple suction cups off center in a way that is actually more robust than placing things right in the middle. And so what then happens if you hard code and you say, well, we're just gonna, hard code that once we understand the scene, you go for the middle. Well, all of a sudden, how do you now special case around that? And you're kind of stuck. And so the general philosophy I like is this notion that if you have prior knowledge, don't hard code it into your system. Instead, use it for effectively data generation. Any prior knowledge can usually be turned into a data augmentation or a data generation scheme. And so you might be able to generate a bunch of example grasps that way for thinking about grasping. And they're good training data because they're good. They're not necessarily perfect, but they're good and they'll help you. But I think that's ultimately going to let you keep improving as you encounter more corner cases where a data-driven approach will give you an exception to yet an exception to an exception without if, then, else, if, then, else. It's just the more data speaks for itself, and the neural net will absorb that. And so I think that's really the way I tend to see it in the long term, is use all that prior knowledge to help you train the neural network, because that prior knowledge can help you generate so much data for your neural network.
That's a really interesting way to unify the two ideas. When you approach the types of problems you're approaching, imagining that ultimately you're trying to build a product or a platform that is as general as possible, but there's a lot of kind of custom consulting-ish customization for each individual problem. I'm curious if you could speak to that and how you've approached it.
Yeah, I think that is exactly the trap to avoid. If you try to build a sustainable company, if you get into a ton of one-off consulting efforts, you're just like, you're not building a product. You're not building something that you can repeatedly deliver. And so, but at the same time, whenever you're asked to deliver something to a customer, it has to be what they need. You can't just say, hey, we built not what you want, not what you need, because then they'll just be like, yeah, well, then we don't want it. So
right. This isn't going to be exactly what you need, but it's going to be not exactly what 10 customers need too.
Exactly. So there's a natural tension there. And the way we've been thinking about this is by, first of all, doing a lot of market research. And so as we did the market research, we saw effectively, big picture wise, we saw a recurring theme of more intelligence for robots. And so if we can build something that can make robots understand their environment, react to it, that's going to be able to power a lot of different solutions. But then zooming in on the kind of beachhead, so to say, of where we're delivering our technology right now, we saw that in warehousing, there are really three main applications that we decided to cater to. The first one is order picking. It's where a robot is presented with items that were in storage. It needs to pick one at a time to put it into a shipping container, and then things get shipped off. That's order picking. Then a second one is put walling, or sometimes put to light. In a put wall, what happens is many orders come into a warehouse, and somebody or a robot has gone around the warehouse and collected the items for all these orders. But it might be for 100 orders or even more. And it's all collected, let's say, in a shopping cart or in a bin. And it's not sorted by orders, just they collected everything needed for fulfilling those maybe 100 orders. Now that shows up at a put wall, and now the robot's job is to take one item at a time out of that shopping cart effectively, and then scan it and place it into a temporary storage that is associated with that specific order until that order has been completely filled from that shopping cart. And then somebody behind that put wall will take it and pack it up and ship it off. So that's put walling. And then the third one is parcel sortation, induction sorting, where there's a lot of parcels going around these facilities, and they often need to be singulated because there's a bulk of parcels coming in. Can you reliably place them one at a time onto a conveyor so then it can go through scanners and so forth to be sorted to the right outbound truck, let's say. And so these three are the ones that we're focused on at first, where we can build something that's very general. So anybody who needs a put wall, anybody who needs order picking, anybody who needs induction sorting, we can deliver to that without having to do one-off consulting for each specific deployment.
And are those problem definitions constrained enough that you can, within put walling, for example, you can cover all or the vast majority of the use cases, or are they further constrained by, for example, the individual SKUs have to be in boxes as opposed to loose bolts or things like that? How granular does the strike zone need to be?
Yeah, it's really interesting you asked that, and I'm glad you're asking because I should have mentioned that anyway. So what's so interesting about how we're building this is that, at least what I'm so excited about, is that we're building a single system behind all three application domains. So the same neural networks are trained for put walling and for order picking and for induction sorting. And you might think, well, why? I mean, those are somewhat different problems, but the core is still the same. The core is you look at a bunch of items. Sure, parcels versus, for put wall, often small items, versus order picking, a range of sizes of items. But you're still at the fundamental level looking at a bunch of items and making sure you're picking reliably one at a time, possibly scanning and then placing. And so it generalizes across all three of those. And then within them, as you said, some facilities might be focused on cosmetics, others might be focused on pharmaceuticals, others on apparel, yet others could be focused on maybe electrical supplies and so forth. And again, it's all the same neural network for all those domains. And I think that's actually the best way to do it, because even within a single domain, you cannot cover everything. There's so much turnover on all these SKUs and packaging of the SKUs that you cannot cover everything. You cannot say, these are the 100 items we need to do. Let's have something specific for that. You need to have something that really generalizes. And by building it in an even more general way than, let's say, just cosmetics, you actually build in more expertise into the neural networks about what it tends to see, what makes for an individual object, what is the 3D of the situation it's looking at, what's the best way to approach, to grasp, to remove, and then what's the fastest trajectory to bring from point A to point B, and so forth.
And to be clear, are your models primarily focused on the manipulation task, or whatever the generalization of that? I'm assuming, a given robot might have some set of tools it needs to select, and you need to identify the best contact point and a variety of factors associated with, let's call it manipulation. And then, I imagine that beyond manipulation, there are other parts of the problem that I'm thinking are more like traditional optimization and not necessarily places where you require neural networks. But I guess that's what I'm asking you to correct for me. What's the scope within these three problem domains of the models that you're building?
Yeah, so there's a couple of interesting things that you're touching upon there. One is that indeed, not every item can be picked with the same end effector. And so there are things called tool changers where a robot can change the end effector on the fly and say, oh, actually, I should use gripper now. I should use 2 suction cup grip or maybe 6 suction cup end effector. And so you can switch that as needed, though it turns out somewhat surprisingly, initially not surprising anymore now, suction cups go very, very far in most warehouse facilities. Now, what's also interesting is that the neural network is the same when it's thinking about how to grasp and manipulate its objects, whether it's suction cup or gripper, and independent of the number of suction cups it's using. And this is going a little bit deeper, but the simplest way to think of it is imagine you have a single neural network, the main body of the network that thinks about grasping. You don't just give it the scene that it's looking at to grasp in, but you also give it the configuration of the end effector. And based on the combination of scene and end effector, it decides what to do. And that way, again, you can generalize beyond what's possible otherwise, which is really cool. So you don't have one-off training for new end effectors. No, it's all shared learnings across every deployment, every type of end effector.
And then just punching in with a question here, are you also giving it tabular style data associated with the product, like skew, dimensions, that kind of thing? Or are you primarily focused on visual or sensor inputs?
So that data can often be made available, but not always. We prefer not to rely on it, just because it can be a pretty strong assumption to rely upon that. But I mean, there are places where it can be made available, but we prefer not to rely on it.
Okay.
Yeah. And the other thing you brought up is kind of optimization. Yes, optimization matters a lot. It turns out reliability is key, but then once it's reliable, speed also matters. If your robot, works at half the speed, it's creating half the value. And in a facility like, warehouse or factories and so forth, if you're not keeping the pace, you might be bottlenecking the entire process. So keeping the required pace is really important. And so there's many methods to optimize robot trajectories that can help do things. But actually, things get really interesting once you're holding objects that, might be flinging because they're heavy and they're floppy and so forth. And all of a sudden, you can't go about it as analytically anymore as you would do when you just think about the robot itself. And all of a sudden, learning, which you thought maybe doesn't matter for motion, all of a sudden, actually, learning can matter again to do better than you can without learning.
Interesting. Kind of continuing that example of objects flinging, there's a suction cup. Every once in a while, something's going to drop. Do you consider that kind of out of scope? And, every night a human goes around and picks up all the drop things and rebins them? Or are you also trying to build intelligence into the robots to remediate that, pick up the items that fall, or some other scenario?
Yeah. So what you're getting at there, I think, is at its core why warehouse robotics is such a great place to be. In that you need to be very reliable, but if just every now and then something needs a human intervention, that's okay. If a person needs to spend 10 minutes, let's say, at the end of the day to clean up a couple of things that the robot did, it's no problem. I mean, obviously you don't want the robot to break anything, but if it just puts something next to a bin, it drops it in trajectory. Of course, we don't want it to happen. We want it to be always 100% reliable. But the beauty here is that you can create a lot of value once you are, let's say, 99.9% reliable, which is a really high bar and is very hard to meet.
Mm-hmm.
But 99.9 is not 100%. And 99.9 maybe wouldn't cut it for self-driving. You might not want a 99.9% self-driving car on the road because, I mean, it means, 1 in 1,000 times, let's say it crosses an intersection, if that's how we count, it gets into an accident, that would be 99.9 reliability on, crossing intersections. That's not good enough. You would never deploy that. But if you think about, and that's really where commercialization is what we think about in great detail, is when does a robot start creating value? And so the value creation, in our perspective, everything we've seen with end customers starts roughly at that 99.9 mark. Because a robot would typically do anywhere from 500 to 2,000 operations per hour, depending on the type of station. Some stations have to be faster, some stations have more involvement, like extra scanning and so forth. They're a bit slower. But even at a slow station, a 500 per hour station, at 99.9, it means, well, you are just making a mistake as a robot once every 2 hours. And that means nobody has to constantly manage, babysit this robot. It's, once every 2 hours, sure, let's quickly fix something. And that's creating real value. And that, in my mind, is kind of the benchmark. Is 99.9 is, of course, we're looking to go further than that. Don't get me wrong, but that's where it becomes just, robot is helpful as opposed to robot needs a babysitter.
Yeah. So I could continue on talking about industrial AI and robotics for the entire episode, the entire interview. I've written a bit about industrial AI and I find it a fascinating topic, but I also want to touch on some of the research interests that you mentioned earlier. In particular, you talked about this junction of unsupervised and reinforcement learning and some of the work you're doing there. Unsupervised learning is something that has been a goal from a research perspective for a while for its data efficiency, but it's really played out in big ways in natural language processing recently. Talk a little bit about that junction and where you see it being interesting.
Yeah. So, as you know, Sam, I've been working on reinforcement learning for a very long time, right? And
Yep.
reinforcement learning is, well, it's trial and error learning, and it's something we're very familiar with as humans. When we see a child learn to crawl, learn to run, that's reinforcement learning. And when we train a dog to maybe sit, that's reinforcement learning. When we say sit and it sits, we give it a treat, and if it doesn't sit, we might yell at it, and from that feedback it figures out what it means to sit and acquires that skill, right? Listening and executing. And so that's reinforcement learning. And a lot of the big successes in reinforcement learning that we've seen so far have been in simulation, right? So arguably the most famous success, AlphaGo, right? The best computer Go player and beating the best human players out of DeepMind. Reinforcement learning played a very big role in that because it was playing against itself over and over and over to become better. But it's all in simulation. Same with many video games, a lot of simulated robotics results. But the question is, when you try to transition from simulation to real world, there are a few things you can do, of course. You can say, hey, maybe that my simulator can be perfectly matched with the real world, and that can help you. But ultimately, you want to be more data efficient. You want to not just learn from reward. You want to learn in other ways. You want to not just do something for a minute and at the end know whether you were right or wrong. No, you want to have feedback that's much denser, much more informative. And naturally, reinforcement learning doesn't really do that in its kind of vanilla form. But we've seen, as you said, in natural language processing, we've seen unsupervised learning, which is learning from just vast amounts of text. And so to make the analogy there, maybe in natural language processing, you want to classify the sentiment. Is this a positive or a negative review? Or is this a a correct English sentence or a broken English sentence, things like that. You want to learn to classify that. And instead of just generating examples of positive and negative articles, you would instead first, because that would take a lot of annotated training, that you'd first train on just predicting the next word in a sentence on all the text you can find on the internet. Once you're really good at that, you must have internalized something inside the neural network about language and its meaning, such that now from a few examples, you understand positive or negative sentiment classification. And so the question is, can we do the same thing in reinforcement learning? Can we have this auxiliary, unsupervised task that has a lot of signal that's not directly the reinforcement learning signal, but still signal to learn from for the neural network to then quickly acquire a new skill? And so we've been working on that quite a bit in the last year and a half. And so what we've seen, and it's not just us, also some people at NYU, Montreal, and so forth, we've actually been able to bridge the gap between what happens when you learn. Let's say a robot has to learn some skill, let's say running or maybe crawling and so forth. When the robot has to learn it with having full access to its entire configuration at all times, all its joint angles, its position, its orientation, that's full access, full state access. That always learned pretty fast, but it would learn slow if all it gets to see is a video stream of itself, because that's maybe 100 by 100 image, so 10,000 pixels. It's much higher dimensional than the succinct state description of the robot. And so what we saw is that massive gap, the learning efficiency when learning from access to state, which is quite efficient, compared to learning with access to image input only, was just this massive gap. Mm-hmm. And so the question is, how do we bridge this? And we did it with unsupervised learning effectively. So as the robot is doing its trial and error, instead of only paying attention to rewards and trying to become better based on was this a good or a bad run so far, it is also doing unsupervised learning on the images it's seeing. And what it means specifically in our case is we did something called contrastive learning. So in contrastive learning, what you do is you want to learn what's in an image. But how do you learn it if nobody tells you what's in an image? Well, here's the idea. Imagine you just download 2 images. And you don't know what's in them. You have no idea what's in them. But now, for one of the images, you make a duplicate, but a modification as you duplicate it. So maybe you have an image and you crop it in 2 different ways. So now I have 2 different crops of the same image. And then there's the other one. Now, the 2 different crops of the same image, even though you don't know what's in it, you know they have the same thing in it. And it's different from what's in the other image. Most likely, if you randomly download 2 images, most likely the other image has something else. Mm-hmm. And that's really where the signal comes from. Now you train your neural network to understand that these 2 crops of that same first image, neural network should know that's the same. Doesn't know what it is, but it should embed it somewhere in a space where it puts those 2 close together, and the other image should be put far away from it. That idea turns out really, really powerful. It's been shown to work really well by Jeff Hinton and collaborators, as well as Kam-Ming Hui and collaborators, on doing that on images, followed by image recognition training, and it's very, very efficient. We can do the same thing in reinforcement learning from images. So you apply the same idea. What the robot is seeing now versus what it's seeing at a different time. Well, the thing is seeing now, you take 2 different crops, and that is still the same thing. And the neural network learns that there's 2 views of the same thing and different from the other thing. Very simple idea conceptually, but very, very powerful. You train that way, all of a sudden, you can train almost as efficiently from image inputs as with direct access to state. This one, we evaluated this on the kind of standard DeepMind control suite simulated robotics environments.
Mm-hmm. In the, there's a whole area of research around multitask learning that seems to suggest, although, there's certainly arguments against this, that networks generalize better when they have more to do, essentially.
Mm-hmm.
I'm wondering if part of what you're seeing is the effect of just giving the network something else to learn, as opposed to the unsupervised task contributing to kind of the core reinforcement learning thing that it's supposed to learn.
So you're absolutely right in that multitask tends to help. I mean, it's why when, for example, at Covariant, we train the same neural network across many application domains, because it'll help to train across all those domains, use the same network rather than specialize to each one of them. Same in the research here. When we train a neural network for multiple tasks, often it can do better. But the beauty about bringing in the unsupervised loss is that you can think of the unsupervised loss as multitask, where
Mm-hmm.
the multitask additional thing doesn't require you to do any annotation, doesn't require you to give any reward signals. So it's like the cheapest way to achieve multitask.
Mm-hmm.
In terms of human effort, cheapest way. Still a lot of compute required, just to be clear. Still
Yeah.
a
Yeah.
lot of compute involved.
Yeah. I think the analogy that I was coming from is like in NLP, when you're training BERT or something, and you have this unsupervised formulation of the problem.
Mm-hmm.
The problem that you're trying to solve in a lot of ways is directly related to you're in building the language model. Blanking out the words is like, that's teaching you language. And I'm wondering if there's a distinction between the second task. Is the second task, it just happens to be an unsupervised task,
Mm-hmm.
and the relationship between that and the core reinforcement learning task that you're trying to solve. I'm not sure that I'm completely articulating the question in a clear way, but the idea is the unsupervised tasks kind of core to, does it inform the core reinforcement learning process and that loss, or is it just an ancillary other thing, and it's the multitask aspect or the other task that is what creates value or causes you to increase performance?
Right. So you're actually getting at something that we're working on right now. So let me say a bit more about that. So to very directly answer your question, I think when we use the contrastive loss on a given image compared to an image at a different time, we're not tying it very directly to the locomotion task versus crawling versus maybe sit or maybe push an object. It's not very closely tied to that. I'm inclined to think of it as, it's like learning the vision system of the robot. It's learning to see and understand, that it's seeing the same thing in these two situations versus seeing something else there. But it's not learning about how the world works. And that's kind of what you're getting at in
Mm-hmm.
reinforcement learning. You try to achieve goals. Your robot's supposed to get from point A to point B, or achieve something with the objects in front of it, or it could be in a game. You're supposed to get a high score in the game,
Yeah.
and so forth. And so this whole notion of achieving goals and how the world works, I think is a natural complementary aspect. So imagine you, in the unsupervised sense, you've been able to complement your reinforcement learning to get a bit of a vision system trained.
Mm-hmm.
But now what you also want is effectively a how does the world work system, such that when I'm asked to do something in this world as a robot, I already kind of know how the world works. I don't have to flail my arms a gazillion different ways, and I don't have to learn that if I don't touch an object, it's not going to move, kind of thing.
Yeah.
I know that the world works with contact forces and so forth. So if I want block A and block B, well, block B that's on the bottom has to be on the table first, and then those things are things that don't come from what I just described, the contrastive learning I just described. You need a temporal aspect to it.
Mm-hmm.
And so that, I think, is one of the important next steps. It requires more compute, and that's probably why it's coming a bit later in the progression of research overall. But the notion there would be, can you understand what are natural video sequences? So if you download a lot of video, what does it tend to look like? And that's a very hard problem because video is very high dimensional, meaning that training your neural networks for video prediction or understanding which videos are more related or less related to each other is computationally an intense problem. It's also the kind of problem that, I mean, I'm sure you're well aware, Jan LeCun's been talking about for a very long time when he gives the cake analogy of reinforcement learning as the cherry on the cake, is the reward signal, but the unsupervised is the most of the cake, right? And the icing is the supervised learning. Unsupervised is most of it. What he thinks of is video. In the context of robotics, at least, they think of video. Robots have watched so many videos that they know how the world works. A lot of research still has to be done there, but I think that'll be really important. And then there's the third part. So there's the understanding what you're looking at. It's part one. We made a lot of progress on that. Then video understanding, behavior understanding in that sense, how the world works. The third part is for the robot to have its own skills. And that's where it gets much closer to what you're talking about, is something we're actively working on, which is, can you let a robot just spend time on its own? Just the robot's just on its own in a room or wherever it is. And can you make it spend its time meaningfully? Effectively play. What for children we would call play. You say, oh, kid is just playing. But actually, yeah, kid is just playing. You might say, well, it'd be nice if it did some chores or whatever. But actually, the kid is just playing. It's actually learning about the world. It's the kid now understands, especially young kids, they understand how now objects interact. They understand how the world works from interacting with it. And that kind of play is another important component. If we think about the long-term future of robotics, if we want to get to less supervision, less needing to train everything into the robots, just let them try things on their own.
Why would that kind of play be different from the goal-directed exploration that we do today in RL?
So there is a good amount of work that's already happening in RL on essentially getting this kind of play to surface. So goal-directed exploration is a great example. There's other work that, kind of similar, but it's called then curiosity or something like that.
Novelty,
yeah, essentially you give rewards for experiencing something that you haven't experienced before. And I think that's worked really, really well in environments that are, I would say, somewhat closed. Meaning, if you think about, let's say, an Atari game, which is a popular reinforcement learning benchmark environment, usually there's a right way to play the game, and there's not too many other things you can do, or you die. And that's what I mean with a kind of closed environment. If you're curious and you try to experience new things, well, you've died many times in the game. That's not new anymore. So the new things are the things that take you to the next level in the game. And so there's a very natural alignment between novelty and the actual task that we care about. And that's why curiosity, goal-oriented exploration, and so forth have had a great amount of success. But that breaks down in the real world where there are so many things you could do. Or even in some games like Minecraft, which is becoming a new benchmark that people get excited about for this exact reason. In Minecraft, you can build so many different things. And so just experiencing something novel, you can keep doing that forever and never learn something interesting. And I think that's kind of the next step there. And that's maybe where I think of things like children's play as being a bit different, because it seems like somehow they have a bit more intuition than our current AI systems about what's interesting play, as opposed to just what's novel, but actually not that interesting.
Interesting. I want to switch gears to a paper that you recently posted up on arXiv, Pretrained Transformers as Universal Computation Engines. Tell us a little bit about that work and what you're looking to achieve there.
Yeah, so this paper, for me, it's one of the most surprising things we've done. Usually I feel like when we write a paper, we have a pretty clear intuition and we know ahead of time, okay, this intuition should be leveraged this way in the algorithm, and as a consequence, it should work, and we should be able to take things to the next level. That's a fairly typical research kind of progression. And sure, there's iterations because your intuition might be wrong, but then you refine your intuition and you improve the algorithm. But this is kind of surprising to me because here we didn't really come up with a new algorithm. It was really an investigation, right? So what we did is we looked at pre-trained language models. So what's very popular these days is to, on massive amount of text, train a transformer model, which is specific architecture of a neural network, to do next token prediction in a document, right? And if you do this, it turns out it works really well on other language tasks. And that had been known in OpenAI, Google, Facebook, and so forth. Many results around this. But the thing we were wondering is, well, if it's so good at doing all these tasks it wasn't really directly trained for, could there be something more general it has learned? When it's trained to predict the next token on so much text on the internet, by seeing the previous text, predict what comes next, might there be a more general reasoning mechanism that has been internalized inside this kind of neural network beyond language? And so the way we tested this, we said, okay, let's see if we take a model, train on language only, not train on anything else, and then let's put it to use to now classify images or do a prediction about a protein sequence binding sites, or a simple math kind of problem like compute the XOR of a sequence of bits. And none of these are language tasks, obviously. So you have to do you can't just put the language model in front of it because the language model only takes in language. You can't give it an image, doesn't know what to do. But
they're also not generative tasks. Like we've seen GPT-3 apply to lots of different areas, generating web pages from text, but they all share this common generative, text-based property.
Exactly. They tend to generate something like the things you have seen before, right? Text, right? So this model is all trained on text. We believed that there was a chance that it actually reasons in a more general way, that there's some kind of thing in the neural network that makes it reason about objects that are on its input and then draw conclusions on its output. And that maybe there are general reasoning patterns in there that if we use that reasoning engine and put it in front of an image, it'll also reason about what's in the image and how these things might interact and so forth. Of course, we need to do a little bit of impedance matching. So we take the image, we have to do an embedding. So we just do a linear embedding layer, which is one layer can do almost no work for neural networks, right? That's the whole idea, that we want that pre-trained language model to do all the work. So just a linear embedding layer, pre-trained language model, and then a linear output layer. Again, because we don't want to output words this time, we want to output a decision, what's in an image, or is this X or a 0 or a 1, or is this, will there be a bind here for the protein or not? So just changing the output and input with just linear, single layer. And then one other thing we had to do the normalization that happens inside the transformer network. So there's layer normalization. We had to effectively retrain that to make sure it's on the right scale for the data that comes through now. Just doing that was enough to get surprisingly good performance on these other tasks. And so to me, that was very surprising because it confirmed that when you train this neural network on language, it's actually not that specialized for language at all. If you train on enough language, it's actually internalizing some more general reasoning pattern. Of course, we don't fully understand this yet, but we have this observation here that it has internalized something that's very generally reusable. And of course, we tested. We said, what if we just put a random transformer in the middle, same as the language model, but randomly initialized, so not trained on language.
Pre-trained.
Same architecture, right? Randomly initialized. And it actually does something, which is kind of surprising that it's also kind of capable of doing something, but not as well as the pre-trained language model. So it seems like there's both some power in the architecture being surprisingly powerful in general, and then there's additional power in what you learn on language transfers over to these other domains, which goes back to something that I mentioned at the very beginning. We talked about, what am I excited about? And I mentioned this notion of, well, the human brain is so general, and it seems like some part of the brain that's normally used for one kind of reasoning could be used for other things. Processing of signal from your tongue can apparently do visual processing. People have seen this in blind people also, that they're what normally part of the brain used for visual processing for blind people can be used for audio processing, part of it. And so this kind of reusability, generality, we're kind of seeing nothing like human brain, just to be clear. Human brain is completely not understood and way more advanced than anything we're working on here. But it tried to make progress in that direction of something that's more general reasoning, not special purpose to a specific domain.
When you talk about the random model and the pre-trained model, kind of sandwiched between these linear layers, are you freezing the transformers and then fine-tuning or training the linear layers in a supervised manner for the specific problem? Is that the idea?
Correct. So once you have the supervised task, you freeze the transformer except for the layer norm parameters, and the linear input and linear output layer. So those get retrained. I think it's about like 0.1% or something of the overall parameter set is being trained that way.
And then when you say surprisingly good performance, does that mean state of the art on some task, or we're surprised that it worked at all, but it's not particularly useful or state of the art?
It wasn't state of the art. It was state of the art in terms of this kind of research. Beyond state of the art in terms of this kind of research, where you're not allowed to train on the task you care about, or not much, only those linear layers. In that sense, yes, absolutely state of the art. But in terms of, if you say, I want the best in the world image classifier,
right.
Am I going to first train on language and then only have a linear layer in the input and the output to work with? No, that's not yet, or maybe we'll never, I don't know, give us the best in world image classifier. No.
I just want to make sure I was not making assumptions on what surprisingly good meant.
Yeah, what I meant with surprisingly good is surprising that it even, that it does much, much better than chance. So, yeah.
Awesome. And where do you see this particular line of research going? What are the next steps?
So I think there's a lot of opportunity in research on multimodal data. And of course, the work I mentioned here is one work. Another work that stands out that I'm sure you've seen is the CLIP work by OpenAI, where they specifically trained at the same time on language and images. So it was trained simultaneously on language and images, not just trained on one and it also works on the other. But that's often the case. Often you have access to multiple data modalities that are, in some sense, not perfectly aligned necessarily, but that are clearly related, and you can co-train them.
Yeah.
I think there's a lot of opportunity there. I think there is a lot of, this could be audio and video that could be trained on at the same time. This could be text and images. This could maybe if you think about robotics, the same things. It could be audio, video, but it could maybe also be sent someday if we have a better olfactory artificial sensors, and combine that with other percepts. I think there's a lot of opportunity to learn unified representations that could probably go further than when we train on each separately.
Great. Well, Pieter, it's been wonderful catching up with you. Appreciate you being so generous with your time and sharing a bit about what you've been up to. Very cool stuff.
Well, Sam, thank you so much. This was a lot of fun.
And actually, I guess before we close out, I mentioned this up front, but you've joined the podcaster brotherhood and sisterhood. We won't talk too much about it, but what's your podcast? What are you trying to do, and where should folks go to find it?
Yeah, so just a few weeks ago, I started my own podcast called The Robot Brains, and you can find it on Spotify, Apple, and so forth. Just The Robot Brains, and having a lot of fun meeting. What we're really focused on is guests who try to bridge the gap between research, AI research, and bringing AI into the real world. That's kind of the general theme. I think it's a really exciting time to see AI transition in many, many places into the real world. And so a lot of the discussions are centered around that. But, it also goes from there to other topics, generally AI research, robotics research, and applications.
Very cool. And I assume it can be found on Spotify, Apple, Google, all the usual places.
Right. Just look for the Robot Brains.
Awesome. We'll link to it in the show notes. Thanks once again, Peter.
Thank you, Sam. Thank you so much for having me. This was a lot of fun.
Thanks.